we'll go. All right, welcome everyone. Today's speaker is Mariam Beriashvili, and she will talk about 2-point sets and other non-trivial point sets.
Okay, thanks, David, and thank you very much to invite me here. It's really the big opportunity for me. And today I will be talk on 2-point sets. In my talk, I will be called 2-point sets the Mazurkiewicz sets. That's why this set was constructed by Mazurkiewicz, and I am always will be say Mazurkiewicz set if it will be no problem for the other people. Okay, and now what will be which special point I will be considering. In my talk, I will be discuss the special point sets such as Mazurkiewicz set, which is called 2-point set, uniform set of the plane, Hamel basis, and Bertin sets. The main topics will be Mazurkiewicz set and uniform set, but I need the other sets, I mean the Hamel basis and Bertin sets, to make the relationships, to show relationships between them. Okay, I will be start now. What about the Mazurkiewicz set? In 1914, Mazurkiewicz presented the transfinite constructions of a subset of the Euclidean plane, and he presented this set, which is called now the Mazurkiewicz set or 2-point set, and how we can to define it. A set M, it's called Mazurkiewicz subset of the plane if cardinality M intersects to L, it's equal or always to. Here L means that every straight line in the plane. Okay, it's this very strange object. I mean, by intuition, that there exists a set in the plane which meets every straight line just in exactly 2 points. Okay, now I need some auxiliary notions for our discussion, and I will be now make definitions. Let MR square be a class of all non-zero sigma finite translation invariant measures on R square. It is a very big class. I mean, it's their cardinality is really big, and we say that any set let X be any subset of R square, it will be negligible with respect to this class if these 2 conditions are satisfied. If there exists measure nu such that X is in domain nu, and for any measure from this class, the relation that if X is in domain mu, it implies that X is null set, and measure of X is equal to 0. So we called such a set negligible sets. Now, a set, right, it's called absolutely negligible if with respect to the same class, if for every measure mu, there exists an extension mu prime of mu such that if Y is in domain mu prime extends mu prime Y will be 0. Okay, the Y set will be a null set with respect to extension of mu. If this set is absolutely negligible, then we can conclude that it will be also the negligible sets. But the converse assertion, it's not true. If the set is negligible, it's not implies that it will be absolutely negligible. The next definition is that the set it's called almost invariant if cardinal T is equal to continuum and cardinal of H plus T symmetric difference of T it's less than continuum. Here H is any vector in the plane. A set W is called lambda 2 thick. Here lambda 2 is standard Lebesgue measure, 2-dimensional Lebesgue measure. If B intersection W is not empty. Here B is a Borel set which measure is more than 0. Okay, the lambda 2 thick sets are very interesting when we are studying the measure extension problem. and that's why the lambda 2 thick measures plays some important role there. Now, the first lemma about the Mazurkiewicz set, that every Mazurkiewicz set are negligible with respect to the class of M, class MR square. It is non-zero sigma finite invariant measures class. Here, every Mazurkiewicz set are negligible with respect to this class. Okay, next lemmas. I will be just say definition of Hamel basis. When we are saying that there is a Hamel basis, we mean that we have a basis of R constructed as a vector space over the rational numbers. Yeah. Every Hamel basis of the space Rn is absolutely negligible subset. There exists a Mazurkiewicz subset of the plane, which is a Hamel basis of R square. I think it is really interesting lemma that we can to prove that we can find such a Mazurkiewicz set which is Hamel basis. I will be try to prove this lemma on the board if it will be visible. I will be trying. I have not in my presentation, but I want to prove it. Okay, it's okay.
I think so.
Okay. Now I will be starting. So I want to prove that if C is Mazurkiewicz set, then it will be also the Hamel basis. It's visible or not so good?
We can just barely read it, I think.
Okay.
Well, you can enlarge your side picture so that it's bigger.
Oh, I see. Okay, yeah, I think it's fine.
Okay, all right. Now, let us start that we need to construct a transfinite induction. And let alpha be at the least ordinal number of cardinality C. And let us construct family sequences and alpha sequences, which will be consisting of all straight lines in the plane. And I will be denote this such LC, such that C is less than alpha. I need an alpha sequences consisting of all points in the plane, and I will be denoted zeta C, C is less than alpha. Okay. Without the loss of generality, we can assume that the partial family of LC, C is less than alpha, and C is odd ordinal contains all straight lines. And when C will be even, then it will be contain all points. C is even. Okay. Here we have, when we have the odd ordinal, we have the straight lines, and when we have a even ordinal, we have points. Yeah. Okay. Now I will be. Okay, I need this such a symbol L. For example, YZ. It will be the plane. It will be the straight line, which passes to the point Y and C. Okay, now we need to construct such as increasing alpha sequences of the sets. Set C is less than alpha. It will be the subsets of R squared, increasing subsets by inclusion, for which will be satisfied the conditions. Okay, the first condition is that the cardinality of ZX will be less or equal to the cardinal xi plus omega. Okay. Now
Sorry, I thought the Z x's were points.
no,
Were they sets of points?
It is a big Z. Okay, sorry, I will be denote the Y. Okay, it means that it is the sets. The small sets are the points, but the big sets will be the sets. Let be it's Y. Okay, it is a set. Increase. We have alpha sequence of sets, subsets of the plane, and
Well,
I need
all
some
the
conditions.
subsets, or
No, I mean how which subsets, which will be satisfied some conditions, and I will be now say which conditions will be satisfied.
oh, I'm sorry. Okay, yeah, okay.
Okay. Okay. Now the next condition, what I need, that every set Y say will be here. It's linearly independent over the field Q. Okay, linearly independent over the Q. Yeah. Okay, the next condition is that every YC is a set of points in general position. General position. The next condition is that if this odd, if C is odd, then cardinal YC intersection LC it's equal to, and if C is even, then this the point that C belongs to the linear whole over Q of the set by Z. I will be not write this. Okay, it's the least condition is that the point zeta C should be belong to the linear whole of the set by C. Okay, I have constructed such a alpha sequence of the subsets of plane, and now I try to show that such alpha sequences give me the set which will be simultaneously Mazurkiewicz set and homomorphism. I think I have a time, or how many time I have to for my talk. It will be okay if I will be proof this to the end, or
I think so. Yeah.
yes. Okay.
You've used less than 15 minutes so far. So
okay.
I think.
Okay. Perfect. Okay. Now I will be suppose that for an ordinal C, the partial family. The partial, I will be right here, the partial family, right, zeta, when zeta is less than C, has already been constructed and satisfied these conditions. Let us put that.
Oh, sorry, are the Y's increasing as the ordinal increases?
No, by inclusion. I mean that they are sets and they are increasing by inclusion. Okay, and we just put that YC will be the union of Y zeta. Zeta is less than C. Okay.
So we can't see that anymore.
Sorry, I will be right. Yeah. Okay. The YC will be the union of Y zeta, or zeta is less than C. Okay. Just we need to show that it will be linear independent over Q, and it's a sign, and it will be in general, but set will be of points in general positions in the plane. Also, it is set. if we will be look the cardinality of T set, or I will be right here.
I suppose in general position means that there's no line, that there's no more than 2 on a line, I guess.
Yes, on the line.
Okay.
Yes.
I thought so.
Yes. Okay, and cardinality, it will be the cardinal C plus omega. Yeah, it's clear. Now we should to consider 2 cases when C will be odd and when C will be even. In the case when C will be odd, we take the straight line LC and claim that there exists a subset T of for LC such that we need the T subset of LC such that by C intersected. Yes, sorry, T is subset of LC, and yes, and we need the union here. T, it's linear independent over Q, and it will be the set of points in general position. And it is first what we should do that it's linear independent and the points are in general position, and then we should to show that Y C union T intersects LC. It will be just exactly 2 points. From here, we know that it is less than cardinal C plus omega, and it is less than C. And from the fact that the line LC contains continuum linearly independent points over Q, it is an equality holds true. Yeah. Now we can define such an equality. Okay, now we may define such a set like C, which will be like C union T, and T is the subset of LC. That we know that cardinality of T by our assumption will be less than 2 here. And also the cardinality is that like C will be less than cardinality C plus omega. Okay, we have this our inequality which we need for our next discussion. Now, if we consider the C ordinal when it is even, in this case we have the sequences of points, theta points, and if we take the points theta C, see here is even, and we just put we have this point, and if the taxi belongs to linear whole over Q of the set, like C union, let's say that theta is less than C, then we define like C set, which will be okay. Let's just consider the situation when theta C is linearly independent of the set like C. In such a situation, we introduce the following notation. We need the following notation that, let's see, it will be the vector. It will be the vector space over Q generated by like C, which is a vector space. I will just a vector space just right here, generated by like C. Okay, and we may write that's the cardinality of. Let's see, it will be then less cardinality C plus omega, and it will be less than continuum.
Sorry, could I ask? I'm
Yes.
going back to the first part. So you want your sets YC to be linearly independent over Q.
Yes,
And
yes.
you've also got this. So what happens at the very first stage? If your very first line is the vertical line and you want to choose 2 points on it, I mean, no 2 points are linearly independent over Q. So how do you do even the first line?
The first line, do you mean, sorry, that's LC, which
Okay, so
I have taken?
yeah, so suppose your
When-
first line is just the vertical axis.
Why are they not? Why are there not independent points over Q in there? It's over Q.
Oh, I see. It's over Q.
Yes.
I see. Yes, yes. Okay, sure. Okay, sorry. Yeah, please go ahead.
Yes. Okay. Okay. Thank you. Thank you, David. And now, yes. Okay. The cardinality of UX will be less or equal to the cardinality of C plus omega, and it will be always less than continuum. Now, I will be defined here. K1 set, it will be union of such straight lines, set and set prime. So this set will be in like C, sorry, like C, and also the Z prime will be Z, and Z prime will be in like C, and they are not equal. Okay. The next set which I need, it will be ZC plus K1, and K3, it will be the union of such straight lines, which will be passes to, I have here C ordinal and the point Z, and Z is from YC. Okay. Each point zeta is in YC here, and T symbol denotes the straight line which will be which passing through Z here, and will be parallel to the non-zero vector zeta C. Here, yeah.
Pardon, to which vector?
Zeta C. We have a point, and we can construct the non-zero vector over the point, yeah. And it will be parallel to this vector and passes to the point theta. And now we can make the union of these three sets, and let us denote this by K. It is yes, it's clear that it's union of straight lines, and the total number it will be strictly less than continuum, yeah, the total number of which is strictly less than C, and we can, this cardinal will be strictly less than continuum, and we can deduce from here that cardinal r squared minus k will be equal to c. Yeah, it will be strictly less than continuum. Now we can write that we have a UXI set, which was the vector space over Q generated by YXI, and let us write such a cardinality r squared minus k union UXI and union UXI plus zeta-xi. It will be, yeah, from here it will be equal to continuum. If zeta is an arbitrary point from T set, then we can write that zeta union zeta minus zeta-xi and YXI be a set of points in general position. Yeah. Okay. And now we should choose such a point zeta prime. So from this difference, that zeta prime union zeta prime minus zeta-xi, and here will be also the union YXI. It should be, we should define such a zeta prime, and the union should be linearly independent over Q. It's to find a point zeta prime, we can choose two rational numbers p and r, such that okay, we need to choose the p and r from Q, such that the p times the prime plus r times z primes minus zxi. It will be in UXI. It is a vector space over Q generated by YXI. From here, we can claim that necessarily it will be the quality that P and R should be zeros. Yeah. Okay. Now, if we need the Z prime show to that existence such as Z prime. Let us consider the family of points. Zeta E is in such a family, which will be this set here. I will be not again write this point family are from this set, and here the cardinality of I will be equal to continuum. And let us put that zeta E minus zeta. Yes, it's not in UXI. For any two districts indexes E and J from the set I from here. Let us suppose the contradiction to our assertion that there exists no such as Z prime, which we need for our proof, and then we get that P. Okay, I should PI Zi plus Ri Zi minus Zc will be, it is a contradiction, yeah, will be in Xc. If such does not exist, where Pi and Ri are such that the sum of them are not equal to 0. Okay, it should be more than 0. Okay. So we can write here the if such a Pi and Ri exists, then we can for each index I, then we can to find such a two rational numbers P and R. So if for every index there exists, then we can to find such rational numbers which will be more than 0, and we can write that P, where is this here, P Zi plus R Zi minus Zc will be in Uxi, and P Z plus R Z minus Zc will be also in Uxi. And from here we can deduce that P plus R times Zi minus Z is in Uxi. And we obtain a contradiction because P plus R is not equal to U, and Ux is vector space over Q. So this contradiction shows that we may put we can find Z prime such that we can to construct YC. So it will be Z primes. Z prime minus Zc union YC. And such a Z prime point for the family, we can to find the we can find family such as points, and we can write that Zc will be Z prime minus Zc. We can write it just, it will be easy to the point, and we know that this point belongs to the linear whole of the set Yc. So if we continue this process, we will become the family such that Y exists, which will be subsets of plane for which all conditions which we have in the I will be right here, 5 conditions will be satisfied. And now the last step is to define the set, Y set, let be it union such Y C is less than alpha. And we can to sketch check that it will be the set which will be simultaneously the Mazurkiewicz set, and it will be simultaneously the Hamel basis. It means that it will be basis of R over Q, and it will be the set which meets every straight line in the plane exactly in 2 points. Okay. I'm so sorry, it was so long proof, and I hope it was interesting. Now I will be continue on my presentation, and I will be not more. If there is any questions, or I think it was not. I like this proof. That's why it's not so hard, but the construction is really easy and so beautiful for me. And I hope I have presented it, but my board is not so big, and it was not easy to just write all formulas or expression already good. So I'm so sorry for this. And now the next theorem. Okay, thanks. Now, the main theorem about the Mazurkiewicz set is that there exists a Mazurkiewicz subset, which is absolutely negligible with respect to this MR square. Now, I need some auxiliary lemma for the next statement that if let G, A, and B satisfy the following conditions, such as G is a subgroup of additive group and their cardinality is less than continuum, A is such a subset which cardinality is less than continuum, and B is Lebesgue measurable subset which measure is more than 0. Then there exists a point C from B such that G plus C intersect to A is empty set. For any two distinct points, A and A prime, there is a line which passes through these 2 points, does not intersect the orbit G plus zeta, and for any two distinct points, X and Y from this group G plus Z, the line LXY does not intersect the set A. It is a there exists such a A and B and G which satisfy the conditions. Now we can prove that if gamma is any countable, infinite, non-collinear subgroup of R square, then there exists a Mazurkiewicz set such that gamma plus Z has the following property. For any countable family, here H means the vectors in R square. For any countable
Sorry,
family of vectors,
what is a non-collinear group subgroup?
It means that it will be in we can check that the straight lines in the graph in the group here. If we have this group, subgroup of additive group, we can find the subgroup in which we can look to the straight lines, which will be non-collinear. It means it will be not coincident straight line in this group in the plane.
Oh, it's not essentially just on not on a straight line. Okay.
Okay, and there exists such a countable family of vectors which satisfies the condition that HM plus gamma plus Z intersection of this family will be lambda too thick in the plane, and the quality and the cardinality of these intersections will be equal to continuum. And the main result, let zeta and gamma be is in the previous lemma, then there exists a measure nu in the plane such that nu is extension of Lebesgue measure, nu is translation invariant, and gamma plus Z is in domain of nu, and R square minus gamma plus Z will be null set in the plane. This theorem says us that there exists such a Mazurkiewicz set which is not absolutely negligible. The previous result was that there exists such a Mazurkiewicz set which is absolutely negligible, but there we can prove already that there exists such a Mazurkiewicz set which will be not absolutely negligible. So in general, character of Mazurkiewicz sets are so strange that all Mazurkiewicz sets are negligible. There exists Mazurkiewicz set which is absolutely negligible, and there exists Mazurkiewicz set which is absolutely negligible. So more precisely, so we tend to say that a very complicated descriptive structure has a Mazurkiewicz set. It means that we can find such a Mazurkiewicz set which is Lebesgue measurable, and their measure is equal to 0, and it is of first Baire category. On other hand, we can find such a Mazurkiewicz set which is Lebesgue non-measurable and does not have a Baire property. And if there exists a Mazurkiewicz set which is analytic, then it is oral in the plane. Okay, it is what I wanted to say about the Mazurkiewicz set, and the next set, which is connected to the Mazurkiewicz sets, the class of Mazurkiewicz sets is uniform sets, and this definition of uniform sets is comes from Luzin. It's the thesis terminology of Luzin, which is called in their book in collected work here. And we call this subset of the plane an uniform in the direction E vector if for each P prime line parallel to E vector we have inequality that cardinal of P prime intersect X is less than or equal to 1. If the set satisfies this condition, we say that X is uniform set. In general, all graphs in the plane is uniform in direction y-axis. Yeah. So, and Luzin posed a problem many years ago. He posed the problem, and he asked that there exists a function such that the whole plane can be covered by countable many isometric copies of the graph of phi. It was really interesting question for mathematicians, and the first who answered this question partially it was the Sierpinski. He has many works about this problem, and assuming the continuum hypothesis, he proved partially that we can find such a uniform set. In general, Sierpinski proved that assuming continuum hypothesis in the plane, there exist two subsets, A and B, such that A is uniform respect to y-axis, yes, and x-axis, and B is uniform with respect to y-axis. Then there exists a countable family of vectors of translations of plane, for which we have that union of these translations. It covered the whole plane. It was a partial because he assumed the continuum hypothesis, but in the frame of CFC, without the continuum hypothesis, it was proved by Davis in 1963 years that there exists countable family of vectors such that there exists the family of subsets of the plane such that the union, countable union, covered the plane, and for each I, the xi is uniform in direction of I vector. And his theorem give us the positive answer about on the Luzin question that we can find such we can find the uniform subset of the plane which countable many transformations covered the whole plane.
So sorry, why is this a solution to Luzin's problem? He asked for
okay. Yes, he asked. We can't. I will be right on the board. Okay, it will be more easy for me to explain. Okay. Now. Okay, we know that there exists this family, the xy's, and let us denote that delta q be open unit square, coordinate square in the plane, and we have the xy, which is set in the Davis theorem here. Now let us make notion x star I being the intersection of xi to the delta q and delta q is open unit square. Now we can define the transformations. There exist transformations in the plane. Y such that gy x E star will be the subset of two 2i plus 2. It is open interval Cartesian here. We can define such a transformation of xi stars because it is unit square and it's okay.
I'm sorry, I'm a little lost. What is delta Q?
It is a open unit coordinate square in the unit.
Open unit what?
I mean the square, delta square, but
Okay.
open in the coordinate.
Okay. Yes. Okay. Thanks.
Oh, so you're going to paste together the countably many uniform sets on each interval. Is that, I guess, what you're doing?
Sorry,
So your idea is to paste together the countably many uniform sets and make it into a single function.
Yes.
Okay. So I see. Okay, that's fine.
Okay, I can now, and the theorem of Davis give us the positive answer on the listening question. And now let us define the finite set in direction vector E. It let be an arbitrary non-zero vector, and we will be saying that B is finite in direction E if this inequality holds true here. For L is here any straight line parallel to the vector E. And the next theorem is, we have the next theorem that if set is finite set in direction any vector in the plane, then there exists an uniform set X in the same direction such that set is countable many P2 configuration of X. Okay, we can present it this finite set with the uniform sets.
What is a configuration? Can you go back for a second?
Oh, yes, I will be invariant configuration. It's a group of all translations of the plane here. Denote the group of all translations of the plane. We have the translations, such as translations of the uniform sets, which give us the finite set in the same direction. Okay, now about the measurability for properties of the uniform subsets that we denote. Okay, we need these auxiliary definitions that we have absolutely measurability, we have relatively measurability, and we have absolutely non-measurability, which means that we consider the measurability with respect to the class and not with a measure, and we say that it is absolutely measurable with respect to class if for all measure from this class it will be measurable, and so on. I will be not detailed to define these definitions, and here Pi2 denote group of all translations here, and lambda 2 is standard Lebesgue measure. Then there exists a P2 invariant extension mu of Lebesgue measure such that all uniform sets in direction y-axis are measurable with respect mu. Uniform sets in direction y-axis, it means that we have a graphs of the functions. Okay. And from here, we can say that any uniform subset is relatively measurable with respect to the class of all two translation invariant measures. If we consider just class, the whole class of this whole measures class of extensions of Lebesgue measure, it will be relatively measurable. And under CH,
I don't know what, is that one of the definitions that you skipped?
Relatively measurable.
Yeah.
Here. If there exists at least one measure from the class with respect, it will be measurable. We need from the class, okay? It will be relatively measurable. Now,
absolutely non-measurable is just
it is that there exists no one. There exists no one measure from the class, and it will be absolutely non-measurable.
Okay.
This class of measures will be defined in the different sigma algebras of the ground space, and it will be a really huge class of measures. And so we need some additional definitions to relatively measurable. Yeah. Okay, and under C8 there exists a set uniform in directions y-axis such that if B is uniform in direction x-axis, the union of A and B is absolutely non-measurable with respect to the class of all P2 invariant extensions of the Lebesgue measure. Yes, we can define such that two uniform subsets of the plane, which union will be absolutely non-measurable to the class of extension of Lebesgue measure. And there is results about finite measures, which will be published by Javakhishvili. And it shows that if X is finite in some direction, then sorry, here should be X. X is negligible with respect to the class of MR squared. If it is finite some direction, it will be always negligible. Okay, now we had the previous lemma in the when we have started.
What is finite?
Sorry?
What does it mean to be finite in
finite? It means that cardinality of intersections x with the L is straight line in direction A is less than omega. I will be showing the definition here. Here is definition.
So could you move the hand away? Is that an omega? Or
omega is
there, yes, okay. So it's not bounded finite, it's just finite. Okay.
Yes, just fine. Here can be any number, for example, 5 or 6. For example, if we can do consider 2 and so on. Now, we know that I have said already that every Hamel basis are absolutely negligible subsets. That's more general results about this will be that for any natural number, if Hn is the set of two vectors whose representation with the Hamel basis H contains at most and 0 non-zero rational coefficients, then each set Hn will be absolutely negligible. Okay, and yes, and its main result, there exists an uniform subset of R square, which is Hamel basis of R square. His proof is that I have written on the board. It's similar, where it's a little bit differences, but the construction is really similar, and we can show that there exists such a uniform subset. And so, conclusion about uniform sets. The solution of the Lucini problem by Davis and the character of the uniform sets infers that any uniform subset will be P2 negligible and not P2 absolutely negligible. In connections with this fact is intersect next question. There is an open problem. Suppose there exists a subset of the plane which is Pn absolutely negligible, and it will be simultaneously Dn absolutely non-measurable. Dn here is isometric transformations of Rn, and Pn is a group of all translations of the space Rn. And it is open question. If someone will be interested in this question, I will be happy now, but until today it is open. About the Partition sets, I will be decided in the connection to absolute negligibility that there exists a Partition set which is absolutely negligible with respect to the class of all non-zero sigma finite translation invariant measures n. And yes, the Partition set, it is the set that if for every perfect non-empty set, the intersection of P to P is non-empty, as the computation of P to P will be already not empty, then we say that P is Partition set. So Partition set has many interesting properties with the measurable in the sense of measurability. But we can say that class of Mazurkiewicz set in not interesting to the class of Bernstein sets. There exists no one set which will be simultaneously the Bernstein set and Mazurkiewicz set, but we can prove that there exists a Mazurkiewicz set which will be the Hamel basis, and so we can prove that there exists a Bernstein set will be the Hamel basis already. So it is what I wanted to talk today to you. I think the time was enough for me. Thank you again, and now questions if there exists.
Yes, thank you. Thank you for your talk.
I guess it's still an open question whether you can have a Mazurkiewicz set which is Borel. Is that right?
Yes, it is already. It is yeah, open set. Open problem. Sorry.
No, it's still an open. Yeah. Okay. Yeah. Can I ask another? So there's another sort of set in this family, which is a very old one. I'm not even sure who it's due to, but it's the fact that you can decompose three-dimensional space into a disjoint union of unit circles.
It
right?
is. You mean Beriashvili paradox or something else?
No. It's unit circles. So you can simply by transfinite induction doing the same sort of thing that you were doing with this Mazurkiewicz set, decompose three-dimensional space into a union of just unit circles. So two-dimensional. So this is, but well, I guess if you haven't thought about it, but a reasonable question is, for example, is the set of circles negligible, or can you get it to be non-negligible? Questions like that.
It is open question, or
I just thought I don't know. I think the same question whether this decomposition can be Borel. I believe that's an open question, but I'm not sure.
Okay, thanks. Very nice. I think it will be open to try that if it's similar, that can we find the sets which will be, yeah.
But a while ago, you also showed something about co-analytic such sets, right? Isn't that true?
Co-analytic? Do you mean that Mazurkiewicz sets which will be co-analytic?
Yeah, or am I mixing that up? Did you, or you had some? You had a consistency result as well about Mazurkiewicz sets. Or oh, it was about choice, right? I'm sorry. So what? Can you remind me what it was? There's a model where you have a Mazurkiewicz set even though you don't have choice.
Yes, it was the co-work with Ralph Schindler, and in this paper it will be shown that there exists a model in which we don't have an axiom of choice, but we have a Mazurkiewicz set. It was very interesting that why that the existence of Mazurkiewicz set implies from axiom of choice and existing of full ordering of R, and we can in this work there is shown that they exist an argument which give us in the model Mazurkiewicz set, and we don't have in this model axiom of choice.
But then the Mazurkiewicz set must be definable in some sense, or not? I mean,
no, I think that it don't need this definability. Don't need in this case. Miller has also shown that there exists a model without axiom of choice in which there exists a Mazurkiewicz set.
Yes, yeah. He showed there's a co-analytic one.
Yes.
Yeah.
Can I ask about your open problem? So does there exist this pi n absolutely negligible?
Mm-hmm.
And so is there something about the group of in Rn that causes the problem? What is it? What's the difference between the groups in n and the groups in 2?
What is the difference between dn and pn? It is a question.
No, but so the definition of pi n absolutely negligible means you're looking at measures that can be extended so that they're invariant
It
under.
will be Pn invariant. It will be Pn invariant,
Right.
and in the case Dn, it will be Dn invariant measure.
But I'm trying to understand what the difference, why the argument for 2 would not extend to n. So is there something about the groups in n dimensions that
Yes.
that you can isolate that's different in the case of 2 dimensions?
Isolate in 2 dimensions when we have a P2 and D2 groups, and what will be difference between them in the plane?
Right. No, but is there some algebraic or
Yes.
some property that causes the? I mean, can you give us some idea as to why this is an open problem and why it doesn't follow from the case n equals 2 with the same ideas?
I'm not sure that I have understand the question exactly, but I think that it is absolute negligibility should be find such extensions which will be Pn and which will be Dn invariant, and such extensions, to find such extensions, it's not so easy.
Okay, so why not so easy? What's the difference in n and as opposed to 2?
What's the difference? Okay, difference. Okay, the difference is between that algebraic. I mean that what is difference the Pn group and Dn group? I mean purely algebraic difference. How we can define the several groups and their differences. So the properties will be extended in the process of finding this extension. I have not understand your questions.
Okay, well, okay, yeah, maybe there's no simple answer. So, okay.
Well, I mean, for one thing, you have Banach-Tarski paradox in 3 dimensions, right? I mean, I have no idea if this is related to it, but I mean, I don't remember what exactly is pi n actually, and it's just the translations, or
I will show your group of all translations.
Yeah, so I mean,
does it have isometric translation?
So is one of the groups amenable and the other not?
Yes.
Oh, it is. It is a question of amenability then. In dimension bigger than 2, it's no longer amenable. So that causes a problem, I guess. I mean, you're extending measures, so it makes sense.
Yes.
Yeah.
Okay.
Yeah. Mm-hmm.
Okay. Okay, the other questions?
Well, it seems that there's no other questions. So thank you very much again.
Thank you, David.
I'll end the recording.